Hi, in this practice session, we are going to do some problems on number theory. So let's just begin. The first question is a Putnam 1984 problem. So the statement of the problem goes like this. For each integer n greater than equal to 1, let f of n be given by 1 factorial plus 2 factorial going on till n factorial. We have to find polynomials. Find polynomials p of x and q of x such that f of n plus 2 is equal to p of n times f of n plus 1 plus q of n times f of n for every integer n greater than equal to 1. So our function f of n is defined like this, and we have to find polynomials p of x and q of x which satisfy this relation for all n greater than equal to 1, right? So let's analyze this function and try to find out what is f of n plus 2. F of n plus 2 is obviously 1 factorial plus 2 factorial, n factorial plus n plus 1 factorial plus n plus 2 factorial, right? Correct. And what is f of n plus 1? F of n plus 1 is basically 1 factorial till n factorial plus n plus 1 factorial, right? Now, since we know f of n plus 2 and f of n plus 1, we can clearly see that the difference of these two, f of n plus 2 minus f of n plus 1, is simply n plus 2 factorial. And n plus 2 factorial can be written as n plus 2 times n plus 1 factorial, right? So we have this condition right now, f of n plus 2 minus f of n plus 1 is equal to n plus 2 times n plus 1 factorial. Now, if you think about it, f of n plus 1 minus f of n, what will be that? That is actually n plus 1 factorial, right? Because f of n plus 1 has one extra term, which is n plus 1 factorial. So we know this, that difference of f of n plus 1 minus f of n is n plus 1 factorial. And here we have an n plus 1 factorial here. So we can replace that and write it as n plus 2 times f of n plus 1 minus f of n, right? So combining that with the left hand side, what are we getting? We are getting f of n plus 2 minus f of n plus 1 is equal to n plus 2 times f of n plus 1 minus f of n, right? Now, this is almost the solution is done basically, because we can now bring f of n plus 2 on one side and take all the other terms to the other side. So we'll take this, transpose it to the RHS, and you will get n plus 3 times f of n plus 1 minus n plus 2 times f of n. And we can rewrite this as n plus 3 times f of n plus 1 plus minus n minus 2 times f of n. And notice that this is the form in which we wanted our solution. We wanted to find px and qx such that f of n plus 2 was equal to p of n f of n plus 1 plus q of n f of n. And now clearly we can take p of x as x plus 3 and q of x as minus x minus 2, because we have established this identity, right? So we have found two polynomials px and qx for which this is true always for positive integers greater than equal to 1. And that completes the proof. So pretty straightforward problem if you realize the difference of functions, right? The next problem is this one. Show that for each integer n, we have 49 divides 2 power 3n plus 3 minus 7n minus 8. So typically in problems like this, we'll always most probably apply binomial theorem. So let's look at the expression 2 power 3n plus 3 minus 7n minus 8. That is equal to 2 power 3 into 2 power 3n minus 7n minus 8. So that is basically 8 into 8 power n, if you think of this, minus 7n minus 8. And then we will write that as 8 into 8 power n plus 1 minus 7n minus 8. And then 8 I can write as 1 plus 7 to the power n plus 1 minus 7n minus 8. And when you expand 1 plus 7 power n plus 1, you will get 1 plus n plus 1 c1, 7, plus n plus 1 c2, 7 square, plus n plus 1 c3, 7 cube, and so on, till you get 7 power n plus 1, and then you subtract minus 7n minus 8, right? This is where we have applied binomial theorem here, right? And notice that this expression is 1 plus 7 times n plus 1, which is basically 7n plus 8. And then you subtract 7n plus 8 from here. These two get cancelled, and you are left with these terms, right? And notice that everything is divisible by 7 square. You can take 7 square common here inside, and you will get something like this, 7 power n minus 1. This is an integer. So we have proved that 7 square or 49 divides this expression, right? So this is a very easy divisibility question. Always approach such questions using binomial theorem. That is probably going to be your best bet. The next one is this one. Find all positive integers. Find all positive integers such that a power 10 plus 1 is divisible by 10. Is divisible by 10. So how do you think about such problems? So what you have to say is a power 10 plus 1 should be congruent to 0 mod 10, right? The best way to think about it is first isolate what is a power 10. A power 10 should be congruent to minus 1 mod 10. And basically that means a power 10 should be congruent to 9 mod 10, right? So what kind of a should I select so that a power 10 is congruent to 9 mod 10? Now think of a mod 10, you have actually 10 congruence classes, 0, 1, 2, 3, 4, 5, 6, 7, and you can also write, I will just write 8 here, and there is a 9 also, right? So when you think of a mod 10, you have these 10 congruence classes. A mod 10 could be 0 mod 10, 1 mod 10 till 9 mod 10, right? Now, what happens when you take uh, a square, right? If you if you think of a square will basically be of the form here 1. I'm doing a square mod 10, okay? Here it will be 1, here it will be 0, here it will be 1, here it will be 4, 9, 16, and that will become 6, 5, 6, 7 square 49, so 9, and 8 square is 4, 64, so 4. So we are getting a square could be basically 0, 1, 4, 5, 6, 9. These are the possible values of a square mod 10. These are the possible quadratic residues, right? Okay. Now, if a square is 0, 1, 4, 5, 6, or 9 mod 10, then obviously a power 10 would be congruent to 0 power 5, 1 power 5, 4 power 5, 5 power 5, 6 power 5, and 9 power 5 mod 10, right? So let's evaluate that. 0 power 5 is a power 10 is going to be 0. 1 power 5 will get a 1. 4 power 5. 4 power 5, if you think about it, it is actually 4 cube is 64, then 256, and multiplied by 4 is 1024. So that is also 4 mod 10. And 5 power 5, 5 power 4 is 625. 5 power 5 is 3125. So that is also 5 mod 10. And 6 power 5 would be same as minus 4 power 5, which will be minus 4 power 5 is minus of 1024, which will be minus 4 mod 10. So it will be 6 mod 10, right? And finally, 9 power 5 would be equal to 9 power 5, what is it coming? 9 cube is 729. So 9 powers will follow the pattern. 9, then 81, 729, then it will be multiplied by 9, it will end with 1. Right, so mod 10 powers of 9 will follow the pattern 9, 1, 9, 1, right? So 9 power 5 will be equal to 9 only mod 10. So what I'm concluding from this is that since a square is 0, 1, 4, 5, 6, 9 mod 10, a power 10 will also be 0, 1, 4, 5, 6, 9 mod 10, right? So that means if I want a power 10 to be 9 mod 10, my a square should be 9 mod 10, right? And a square should be 9 mod 10. That was coming in which cases? When a was 3 mod 10 or when a was 7 mod 10, right? So what I'm saying is a square is 9 mod 10 if a is 3 or 7 mod 10, right? And if a square is 9 mod 10, a power 10 is also 9 mod 10. Make sure that you follow the argument here, what we have done. So the positive integers which make a power 10 plus 1 divisible by 10 are always either 3 mod 10 or 7 mod 10. That is your answer. These are the cases where you will get the a power 10 plus 1 to be divisible by 10. So that is an application of powers, and we did it by finding the quadratic residues and raising that to the power 5. The next question is this one. Is it true that 3 divides 2 power 2n minus 1 for each positive integer n? Positive integer n. Very easy question. Think about it. 2 power 2n minus 1 can be written as 2 power n minus 1 multiplied by 2 power n plus 1. Now, if you think of the three numbers, 2 power n minus 1, 2 power n, and 2 power n plus 1, these are three consecutive numbers. These are three consecutive numbers, and whenever you have any time p consecutive numbers, that product will always be divisible by p, or at least one of those numbers will be divisible by p, right? So if you have three consecutive numbers, one of them has to be divisible by 3, right? Now, if one of them is divisible by 3, then you should be guaranteed that 3 does not divide 2 power n, because the only prime factors of 2 power n are 2. So 3 cannot divide 2 power n, so 3 must divide 1 of 2 power n minus 1 or 2 power n plus 1. So therefore 3 definitely divides the product of 2 power n minus 1 into 2 power n plus 1. So pretty simple, but this argument, this logic should be clear to you and you should learn how to use it. Let's go on to the next one. If x and y are odd, prove that x square plus y square cannot be a perfect square. Prove that x square plus y square cannot be a perfect square. Great. So if x and y are odd, both of them are of the form of 2k plus 1, or basically 1 mod 2, right? So what will happen to x square and y square if you think of them mod 4? So square this and you will get 4k square plus 4k plus 1. So that is clearly 1 mod 4, right? So what we are getting is x square is congruent to y square is congruent to 1 mod 4. So obviously then x square plus y square will be congruent to 2 mod 4. We are getting this result. Now think of the quadratic residues mod 4, right? X square mod 4. What are the possible quadratic residues mod 4? So when x is 0, 1, 2, 3, what will be the x squares? It will be 0, 1, 0, and when you do 3 square, it is also 1. So what we are getting is quadratic residues mod 4 is only going to be 0 or 1, right? No matter what kind of a number you take, x could be 0 mod 4, 1 mod 4, 2 mod 4, 3 mod 4. X square is 0 or 1 mod 4, right? So that means 2 mod 4 is a non-residue. Or what that means is that there is no number x such that x square mod 4 can be equal to 2 mod 4 or congruent to 2 mod 4. Therefore, since x square plus y square is coming out to be 2 mod 4, we know that x square plus y square cannot be a perfect square. I hope that is clear. X square plus y square cannot be a perfect square, right? Okay, the next problem is this one. Show that for each integer n, this is a positive integer n square divides n plus 1 power n minus 1, right? Again, we'll do binomial theorem. We'll say 1 plus n power n. Expansion is 1 plus nc1 n plus nc2 n square and so on till ncn n power n. And if we subtract 1 from this, 1 plus n power n minus 1, we get nc1n plus nc2n square and so on till ncn n power n. And it is clear that this term is n square. We can take that common. We have 1 plus nc2 and so on till n power n minus 2. And basically, it's an obvious proof that n square divides 1 plus n power n minus 1. Another simple problem. The next problem, however, is more complicated, and I would like you to pay attention. This is a result that will be useful for you in different situations. And we'll do basically 3 parts of the problem. The first part of the problem is this. Let a and b be integers, and let n be a positive integer. You have to show that if a minus b is not equal to 0, basically a is not equal to b, show that GCD of a power n minus b power n by a minus b comma a minus b is equal to GCD of n times GCD of a and b power n minus 1 comma a minus b. So try to understand this expression. The left hand side is GCD of two numbers. What are the numbers? A power n minus b power n by a minus b and a minus b. The right hand side is GCD of n times GCD of a and b raised to the power n minus 1 and a minus b, right? I'm just explaining what it means because the proof is a little tricky here, okay? So we have to show this. Now, how do we start this problem? So let's start like this. We can write a power n as a minus b plus b whole power n. And now I'll do binomial theorem on this expression, and this will be a minus b power n plus nc1 a minus b power n minus 1 b plus nc2 a minus b power n minus 2 b square, and so on till we get n minus 1 a minus b power n minus 1 plus b power n, right? This is my expansion of a power n by using this a minus b plus b trick, right? Now notice that you are getting a b power n on the right hand side, so we can bring this b power n on the other side and write a power n minus b power n is equal to a minus b power n plus nc1 a minus b power n minus 1 into b, so on till n minus 1 a minus b into b power n minus 1. And from here we can divide by a minus b on both sides, and you will get a minus b power n minus 1 plus nc1 a minus b power n minus 2 into b, so on till n minus 1 a minus b is gone from here because we have divided by a minus b. You get a b power n minus 1, right? So now notice that all of the terms here have a minus b as a common factor. The last term here would have been n minus 2 a minus b and b power n minus 2, right? The last term here which we have not written, and this is the final term, right? So all of these terms have a minus b common, so we can take a minus b common and write this as a k plus, it will be the product of some k into a minus b plus this term. This term is basically equal to n times b power n minus 1, right? Because n minus 1 is n. So we are getting this result, right? So I will write that result here. A power n minus b power n by a minus b is coming out to be k times a minus b plus n times b power n minus 1, right? Correct. So this looks like a is equal to b times q plus r, right? In Euclid's division lemma, when we divide a by b, consider this as your capital A, consider this as your b, then this is the quotient and this is the remainder, right? And Euclid's division lemma guarantees to us that GCD of A and B is equal to GCD of B and R. This is theory. Euclid's division lemma guarantees us this. GCD of A and B is equal to GCD of B and R, right? So here we can say GCD of A power n minus B power n by A minus B and A minus B should be equal to GCD of n times B power n minus 1 and A minus B, right? So this is our first result that we have gotten, okay? Now, in the similar fashion, what you can do is you can try to find b power n and write b power n as a minus b whole power n, okay? You write it like this, expand the binomial sequence, so you get a power n minus nc1 a power n minus 1 into a minus b plus and so on, and you get plus minus 1 power n minus 1 n minus 1 a times a minus b power n minus 1 plus minus 1 power n a minus b power n. We have written this binomial sequence in order to get a power n minus b power n in a slightly different way now. So you will take b power n on this side and bring all the other terms to the other side, and you will be able to show a power n minus b power n by a minus b is equal to some L times a minus b plus n times a power n minus 1. How does this come? This comes from here. When you divide a minus b, you will get n times a power n minus 1. It is the same method that we have done in the previous case. There we got a power n expansion and we got this result. Now we are getting this result. You should try and fill in the steps yourself. Okay. So again, we can say by Euclid's division lemma, GCD of this and this will be equal to the GCD of this and this, right? So what I will write here on the next page is this: a power n minus 1, b minus b power n by a minus b, and GCD with a minus b is equal to GCD of n a power n minus 1 and a minus b. And we already got earlier a power n minus 1 minus b power n by a minus b, and GCD of this was equal to GCD of n b power n minus 1 and a minus b, right? So these two results combined basically tell us that the GCD of n times a power n minus 1 and a minus b is equal to the GCD of n times b power n minus 1 and a minus b, right? Because both of them are equal to the same thing. So let's call this number as d. Let's call this as d. Now in our question, what we want to prove is that GCD of this expression is equal to n times ab power n minus 1 a minus b, this GCD, right? We will call this number as g, okay? Our job is to prove that d equals g, right? Our job is to try to show that what we have already gotten, this d was equal to this. We need to show that this is equal to this, right? Okay. So the way we prove two numbers are equal in number theory is by showing that both of them divide each other. If I want to show d equal to g, I need to show that d divides g and g divides d, right? So, okay. So what is my d? D is equal to n a power n minus 1 and a minus b, the GCD of this, or n b power n minus 1 and a minus b, GCD of this. And what is g? G is n times GCD of a and b to the power n minus 1 and a minus b. So we'll start by doing one side. So since d is the GCD of these two numbers, we know d divides n a power n minus 1 and d divides n b power n minus 1. So from there, it follows that d should divide the GCD of these two numbers, because d is a common factor for these two numbers. So the greatest common factor of these two, d should divide the GCD of those two, right? So now this is equal to n can be taken common, and a power n minus 1 and b power n minus 1, right? Which is basically equal to n a and b power n minus 1. These are standard properties of GCD, right? So now we know that d divides n times ab to the power n minus 1. And we also know from here, we also know that d divides a minus b. So again, d is a common factor for this number and this number. These two numbers, d is a common factor. So d should divide the GCD of n times ab power n minus 1 and a minus b, which is equal to g. So we have proved that d divides g, right? Follow the steps carefully. The logic is airtight. We are getting d divides this, d divides this. So d should divide the GCD of those two, which is equal to actually this by properties of GCD. These are standard properties. Then once d divides this and d divides a minus b, it should divide the GCD of these two, which is equal to g. So we get d divides g. Now we prove the opposite side. Okay. So we know that G was equal to n times A and B GCD power n minus 1 and A minus B. And therefore, we know that G divides n times GCD of A and B power n minus 1, right? Correct. Then from this, uh, it should follow that this was equal to what? N times A power n minus 1 and n times B power n minus 1, right? The same GCD can be written like this. So therefore, G divides. Okay. No need to worry about this so much. We'll just rewrite this GCD in a different way. We'll write GCD as n A power n minus 1, n B power n minus 1 GCD and A minus B. So what this means, G was equal to the GCD of these two. So G clearly divides this, right? So if G divides the GCD of these two numbers, it follows G divides n power A, n into A power n minus 1. And we know that G already, from here, we know G divides A minus B. So we know G divides this and G divides this. Therefore, G divides the GCD of n A power n minus 1 comma A minus B, which implies that G divides D. We have already shown that D divides G, and now we show that G divides D, which implies that G equals to D. So the proof is done. The first part of the proof is done. What we have shown as is that A power n minus B power n by A minus B and A minus B, the GCD of this is equal to n times GCD of A and B to the power n minus 1 comma A minus B, right? The second part of the problem is asking us that if A plus B is not equal to 0 and if n is odd, show that A power n plus B power n by A plus B, GCD of that with A plus B is equal to n times A and B power n minus 1 and A plus B. So basically, this is a very simple problem. It's just a restatement of the original proof. We have proved part 1. Now, what I want you to do is set small b is equal to minus b, and we'll have A power n minus B power n by A minus B will become equal to A power n plus B power n by A plus B. And from the first property, we know that GCD of A power n minus B power n by A minus B and A minus B is equal to n times A and B GCD n minus 1 by A minus B. So now this expression will start looking like what? A power n plus B power n by A plus B, comma A plus B. And the right hand side will start looking like n times A and minus B power n minus 1 and A plus B, right? And GCD of A and minus B is the same as GCD of A and B. So we'll be able to prove this also. So from the first statement, if you put B as small b as minus capital B, you will be able to prove the second statement. It is a direct proof. You just have to set it in the first identity and you'll get it. So that should be clear. The last part of the problem is also a little interesting. It says, if A and B are relatively prime, if A and B are relatively prime with A plus B not equal to 0, and if P is greater than 2 is a prime number, then A power P plus B power P by A plus B GCD with A plus B is equal to 1 if P doesn't divide A plus B, and P if P divides A plus B. Now what is this? This is a extension of property 2. In property 2, we had if n is odd and A plus B is not equal to 0, we have shown that A power n plus B power n by A plus B with A plus B, the GCD, is equal to n times GCD of A and B power n minus 1, comma A plus B. This is property 2, which comes from property 1. We have done the full proof of property 1, and from property 1, we got setting B is equal to minus B, we got property 2. Now think about property 2 result, and because we have P is a prime greater than 2, so therefore P must be odd. P is odd and we have A plus B not equal to 0. So it satisfies the condition of property here, right? So then instead of n, I will put P here. I will get A power P plus B power P by A plus B GCD with A plus B should be equal to here P times A and B GCD with P minus 1 and A plus B. Now A and B are relatively prime, so this is 1. You're getting GCD of P and A plus B, right? Basically, now P was a prime, so this GCD is equal to the GCD of P, a prime number, and A plus B. So it is equal to 1 if P does not divide A plus B. If P is a prime number like 3 and A plus B is 8, 3 does not divide 8, then the GCD of these two will be relatively prime and equal to 1. And if P divides A plus B, then the GCD will be P. So basically extending the previous case for n is equal to a prime which is greater than 2, which means n is equal to P, which is an odd number, we get this conclusion. Property 3 comes. So go through the proof of this, all of the three properties in detail, because this is a problem that is fairly common and it has been asked in some Olympiads before, especially the first proof. It is pretty important. So notice how we proved that D equal to G. That's a standard method where you show that each of the numbers divide each other. And that's how you show that they are equal. So that's all that I wanted to share in this video. Hopefully you have learned something. Please make sure that you like the video, subscribe to the channel, and please share it with your friends if you feel like the content is helping you. Your likes and subscribes are going to help me bring more content to you. So please do that for me, and I'll see you next time.